The Pythagorean Theorem says in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So within the field of construction, if you ask somebody in construction, about the Pythagorean Theorem, they'll probably know a little bit about it. They probably have tools in their toolbox that might represent these Pythagorean triples, like a 3, 4, 5, or some multiple of that. It's a way to guarantee that you have a right angle when you have a 3 and a 4 coming together and a span between the ends of those two, that's a 5, and any multiple of that, you got a guaranteed right angles. It's a way to square off things. So Pythagorean triples are used frequently in ACTs and SATs on testing like that. Even on the tests that we write, we oftentimes use Pythagorean triples, and you can, if you know them, you can avoid even doing the algebra of plugging in the lengths of the legs of the hypotenuse to solve for the missing piece if you recognize the triple. So here's what a triple is. It's actually more useful than you might think if you recognize the ones I list here. But 3 integers that satisfy a squared plus b squared equals c squared. In other words, our first triple is a 3, 4, 5. And if you take and plug in 3 for A and 4 for B, it will equal 5 squared. That's what makes it a Pythagorean triple. 9 plus 16 is equal to 25, right? 9 plus 16 equals 25. One step further so you can see it. And so all the others that I'm going to list here are also triples. And not only that, but you get an infinite number of triples from this 3, 4, 5. Any multiple of 3, 4, 5, like 6, 8, 10, is also a triple. If you multiply it by 3, 9, 12, 15 is also a triple. 6, 8, 10, that's just a multiple of that one. It's not a base triple. 5, 12, 13 is another one. When I give you a list of triples like 5, 12, 13, how do you know which are the legs and which is the hypotenuse?
The legs are the shorter.
Okay. Legs are the shorter of the two. Of the 3. The 2 shorter ones of the 3. And the hypotenuse is always the longest side on the right side. Okay. 8, 15, 17. What else we got here? 7, 24, 25. 9, 40, 41. 20, 21, 29. I'd say I know these first 5 in the list. I didn't recognize the 9, 40, 41, 20, 21, 29. I don't recognize those, but those top 4, I think I would recognize them. So if you recognize the triples, you get to avoid doing the algebra to solve for the missing side like you did last year. So here we are in geometry. We're going to use this theorem frequently enough that it is worthwhile to recognize triples. Like example 1a, what is C based on our list of triples? 13, because we got a 5 and a 12, and C has to equal 13 here. And then is there a 7 and a 14 anywhere in this list? No.
Well,
There is, but in the same string of numbers is what I meant. Sorry, 7 and 14. No, there isn't anyone where the 14 is the hypotenuse. At least not in this list. We're going to know in just a minute if it's a triple or not. A triple is these 3 values that satisfy a squared plus b squared plus equals c squared. These are all called, I'm blanking on the name now. I don't remember. Anyways, these are kind of like what I would call base triples. I don't remember what the name is of them, but from which you could get a whole bunch of them. What's that? What? No, there's a specific name for them. I can't remember what it is. But 7, let's see here. We'll know in just a minute. Let's go ahead and solve this using the Pythagorean theorem. Here's what you would have done in algebra. You would have gone, okay, it's x squared plus 7 squared equals 14 squared. And then we're going to go and solve this. We're solving for a leg this time. So we've got x squared plus 49 equals, everybody knows 14 squared, right? It's 196. You got your perfect squares memorized all the way through 20, right? No. Through 12?
Yeah.
Yeah. 15?
I did last year. Oh.
You did last year? Okay. Yeah. So subtract 49 from each side. So I've got x squared equals, let's see, what's 196 minus 49? 47. Is 147 a perfect square? No. So here's where you have the choice, and this is where that little practice worksheet we did yesterday comes in. If it's a real life problem, it makes sense to change it to a decimal. You're not going to go to Home Depot and tell them, I need a board that is square root of 147 feet long, right?
Why not tell something that's good?
You're going to get a decimal approximation and then round it up. Okay, so this is you cut it. But you're not going to go and tell them I need a board that's square root of 147 feet long.
I want to.
You want to, right? Or better yet, that's 6 root 2 feet long or something. But in geometry, okay, guys, in geometry, when we're just doing problems where we're solving, or in trigonometry, I should say, we're more specified now. Right triangle trig. If you're just solving a right triangle and you're trying to find exact values, you might leave it in simplified radical form. So now you got to make the decision. You could find a decimal approximation. What is the decimal approximation? Maybe you get it. You hit second and then the x squared button and then 147. Square root of 147, which is, what is it? About 12.13. That's a decimal approximation. We'll use squiggly equals. That makes sense for that picture. Definitely not a triple, right? But about 12.13. 147, if I did what we did yesterday, 11, 12. I know 3 goes into this. 3 goes into it. 49 times that. And then 49 is 7 and 7. So what would this be in exact form in terms of radicals? 7 root 3. Yeah, that's what we talked. So, and that tells me this is actually a special right triangle. Based on what I know about special right triangles, I know what the other 2 angles are, and you'll learn about it. This is lesson 2, chapter 8. So this is a 30, 60, 90 triangle. And I know that based on the ratios of the sides. So the 7 root 3, the 7, and the 14 tell me what the degree measures are. So geometrically speaking, or when it comes to trig, right triangle trig, we're going to be leaving it in simplified radical form unless it's a word problem. Does that make sense? So if it's a word problem, you can change it to a decimal. It makes sense to change it to a decimal. It's a real life problem. And if it's not a word problem, not a real life sort of problem, then just leave it simplified radical form. You got to be able to do both. Okay. Find the area to the nearest tenth. Okay. Find the area to the nearest tenth. So this one, it's a real life sort of problem. It's the area of some shape here. So we're going to go ahead and get a decimal approximation on this one. So there's the key. We just drew in an altitude to that trapezoid. This is a trapezoid. We're going to break this trapezoid into a triangle and a rectangle. It's like, I don't remember the area formula for a trapezoid. Actually, I do, but I'm going to pretend if I didn't remember it. But I do know the area formulas for triangles and rectangles. So we're going to break it into 2. And we're going to use what we just learned here. So if this whole thing is 16, do you see how we got 6 down here? That's a little 6 right there. Up here is 10. So this portion from here to here is 10, right? It's going to match that straight across. So that makes that 6. Let's call this x. And let's use a little Pythagorean triple magic on this guy here. There it is. What goes with 10 and 6? 8, right? 8. It's a Pythagorean triple. Now you can go through and do what I just did on example 1b if you'd like, and you'll come up with 8, right? The setup would be 6 squared plus x squared equals 10 squared. But if you really are familiar with your list of triples, and it's worthwhile being familiar with them, I promise you, when it comes to standardized testing and high school mathematics, it's worth it to know it. But you'll get 8. So x equals 8. So here's the deal. The area of this shape is going to be equal to 1/2 base times height plus base times height of that rectangle. If I were to draw a pictogram of this, area is equal to this guy, here's my pictogram, plus this guy. And that'll make more sense, right? It's equal to this right triangle here on the left plus the rectangle on the right. And what's the area of the right triangle on the left? It's 1/2 base is 6, height is 8, plus what's the base of the rectangle on the right? 10 and the height of 8. So there's our little pictogram, and then plugging in the values. So area equals Half of 48 is 24, plus 80, 104 meters squared. So I don't need to round them to 10, but it would make sense on this one if you're finding the area of a shape. It's sort of real life. Round it off to the nearest 10. If you're finding area for the purpose of painting or constructing something, you would want a decimal approximation of it. You don't want to leave it in radical form. Although it would be fine to go into Home Depot and ask for a board that's 6 or 2 feet long instead of an 8 or 10 footer. I like them at 6 or 2 feet. See what they do. All right. So there's an application of the Pythagorean theorem, actually of Pythagorean triples. So proof of the Pythagorean theorem. There's quite a history on proof of the Pythagorean theorem. I think Pythagoras got his name attached to it because he first proved it, although it was used before him. But one of our presidents from the past, James Garfield, put together a proof of the Pythagorean theorem that was different from this. This is one version of a proof of the Pythagorean theorem. There are many of them. Okay, this is a picture version. Here's the deal. We've got I gotta pick a different color here, maybe green. So we've got this square inside of a square. Here's how we're going to label it this way. Here are right angles here. We're going to label this A, this B, and this C. And we're going to set up an algebra equation here. Do the algebra, and out will pop a squared plus b squared equals c squared. Here's how it works. Would you agree that if that's A and that's B, this would also be A over here? Yes. Okay, we're going to assume that these triangles are all congruent, actually. That's how it's been drawn. So this would be B, this would be A, this would be B, this would be A, this would be B. Okay? So if I wanted to find the area of the outer square, the area of the outer square would be represented by A plus B quantity squared. And I'm going to state that this is equivalent to the blue square in the middle plus the 4 areas of the right triangles surrounding the blue square. The blue square in the middle, we're going to call it C squared. Do you see why? Side length of C, so it would be C by C or C squared, plus 4 times 1/2 AB. And here's why we have 4, 1, 2, 3, 4 right triangles with an area of 1/2 AB. So, okay? I'm just telling you that these are 2 different ways to represent the same area. And we're going to do a little bit of algebra. This is from last year. This is called a special product, A plus B squared. The way it works is this. You square the first term, you square the last term, and then you double the product of what's in parentheses. It looks like this. A plus B squared is equal to A squared plus, not just plus B squared. That's what a lot of students think. It's not. I can demonstrate that for you in a minute. But 2AB plus B squared. There is a middle term here. Perhaps you heard that a lot last year. You go, oh, there's a middle term there. Don't just square the A and the B. Okay? A plus B squared means A plus B times A plus B. If you do FOIL, FOIL has F-O-I-L, 4 terms to it. The outer and inner get joined together to make the middle term. Okay, so A squared plus 2AB plus B squared is what that's equal to. Here I have C squared plus, and this becomes, magically, 2AB. And then algebraically speaking, I can subtract 2AB from each side. And we've got the formula A squared plus B squared must always equal C squared, because I labeled these generically with A, B, and C algebraic terms. So it wouldn't matter what A, B, and C are. If you have a square inscribed in another square, you have a demonstration of the Pythagorean theorem. So A squared plus B squared always equals C squared. It's a way of just demonstrating that the area built off of each of the legs of a right triangle is equal to the area that would be built off of the hypotenuse. That's what this is demonstrating. Like if you were to draw little squares, drew little squares off of here, I'll do it right down here. I'll do just one of them. I built a little square right here that is A by A, and then another square off of here that was B by B. The area of the A by A square and the B by B square would be equal to the blue square here, the C by C square. So that's what this is demonstrating. All right? It says draw an isosceles right triangle properly. Okay. When we say properly, we mean make it look like it has a right angle and two legs that are equivalent in length. So here's what a proper right triangle, isosceles right triangle would look like. I don't know, I'm trying to do my best. There's a proper right triangle. So it's got a right angle, it's got two legs here and here, x and x, which are equivalent. Hopefully they look equivalent. That's what I mean by proper. XX and 18. So we saw this on the little review I did with you the other day. So you did this one. You asked me about this one. I think it's problem number 15 on that little worksheet. So you guys are going to do this on the worksheet when you finish it up here today. We've got XX and 18. And it says, what is the length of the leg? So this one, the 18, I don't think I see an 18 in with my Pythagorean triples that I gave you. There's not an 18 in there. Nope, nowhere in there. So here we are. We're going to go through and figure out what x is. And they're both the same, okay? They're both the same. This is another example of what we call a special right triangle. It's a 45, 45, 90. We'll learn more about that later. But here's what I know. I know a squared plus b squared equals c squared. And I know that a and b in this case happen to be the same thing. So I'm going to plug in x for a and x for b. And just using some algebra, x squared and x squared are like terms, so I can add them. We have 2x squared, and because we know our perfect square is all the way through 20, I know 18 squared is 324. You guys all knew that. 324. There's a math nerd you guys are. 18, you know 18 squared is 324. Okay, so algebraically speaking, I'm going to divide by 2. So I get x squared equals 1. I think I heard it. And then we're going to take the square root of each side. So square root of 162. But we're not going to change it to a decimal because this is going to turn out to be one that we want an exact value for. So we have this square root of 162. So if we come up here and we do our little factor tree like we did on that review worksheet yesterday, break this down, I get, how about 81 and 2. This is actually the way in which I go about simplifying these, is if you can find the biggest perfect square that goes into it, that's more efficient than breaking it all the way down to its primes. Yeah, 81 is a perfect square, right? Remember, we've got this going on. We don't write it. They all have square roots of them. So it is. It's 9 root 2. And so that means this side length is 9 root 2, and so is this side length. And that's always the case with what we call a special 45-45 right triangle, is that those two legs are the same. Okay? I know, I just sit right here.
Wait, wouldn't you break down the 9?
Nope. Square root of 81 is 9. We can't break it down anymore. So we have 9 root 2.
Wouldn't we break it down to 3 and 3?
Nope, because we've already taken the square root. Square root of 81 is 9, so we've applied it already. You could, but you'd end up with actually 4 3s. And so you pull out one pair of 3s, and another pair of 3, and then 3 and 3 is 9. So we end up at the same place. All right. So, man, what do you notice about the relationship between this 18 and the 9 root 2?
You multiply the 9 by 2.
Yeah, I do. And that's actually that's what we're going to learn next time. But if you multiplied the 9 root 2 by root 2, you would actually get 18. Or another way to think about it is take the 18, take half of it, that's 9, and then attach a root 2. That's always going to be the case. I'll talk more about that later. Here's another application of this. If I have a 5 as my hypotenuse here, I want to find the area and perimeter of the square. I know those are each x. So if we do our setup here, we have 2x squared equals what? Whatever 5 squared is, right? Yeah, equals 25. So x squared equals 25 over 2. So x equals, this is kind of interesting here. Here's how it works. It's square root of 25 over square root of 2, right? This is the bottom of the review page we did the other day. It's the rationalizing the denominator. Square root of 25 is a perfect square, so I get 5 over root 2. But here's the deal. I want this in simplified radical form, like these 9 root 2's up here. I don't want any radicals in the bottom. Okay. So you multiply top and bottom by root 2, and your final answer ends up being 5 root 2 over 2. So each of these sides are 5 root 2 over 2 and 5 root 2 over 2, which is interesting because that's kind of the same pattern as up here. It's half of the hypotenuse times root 2. I wonder if that's always true. Come back. Actually, Friday. You have to come back Friday. But for 45, 45 right triangles. So we've got a perimeter. So here's the perimeter. Let me switch colors. Perimeter of this thing is going to be, how many 5 root 2 over 2's do I have? 4 of them. It's going to be 4 times 5 root 2 over 2. Uh-oh. How do we do that? No. Okay. We want it in radical form. You could. Calculator's going to spit out a decimal. No. Oh, you got a calculator. Okay. You got the smart calculator. It writes in simplified math form. So 4 divided by 2 is 2. 2 times 5 is 10 root 2. So you got 10 root 2 meters. And that's an exact form. And you could pop it in your calculator. That's the exact form of the perimeter. The area is equal to 5 root 2 over 2 squared. Okay, because this is a square. So here's the deal. You square the 5, which is 25. When you square the root 2, what do you get? 2. That's what we learned yesterday. Square the 2, you get 4. So we've got 50 over 4. I think we could do better than that. That's equal to 12 and a half. Where did I see that 12 and a half just a little bit ago? Yeah, right here. I could have taken that as my area because x squared is the area of a square, right? So 12 and a half is the area. Makes sense. So here we go. So you're going to be asked to, you're going to be dealing with squares quite a bit, where they'll give you the hypotenuse like I did here. This is going to show up all the time. You got to find the legs. So just use the Pythagorean Theorem. You're welcome to use any shortcuts you're starting to discover. I'll officially give those to you Friday. That's it. Oh. You still copying that down? Sorry. So the area is 12.5. There you go. I got a couple more examples, one more page here. This theorem, before Pythagoras came around, was used in the form that I'm going to show you next. Probably even more often, because they have evidence that they used what later became known as the Pythagorean Theorem when they were resurveying the land in Egypt after the flooding of the Nile, annual flood. Flood and move major amounts of silt around, and so very rich land, and so they were able to grow really healthy crops there. But they had to resurvey the land every year because of that Nile flooding. So this is going in the reverse direction here. The converse of the Pythagorean theorem says if the square of the length of the longest side of a triangle is equal to the sum of the squares of the length of the other two sides, then the triangle is a right triangle. So the question is this a right triangle? With these 3 lengths, is it a right triangle? So you check. 8 squared plus 7 squared, does that equal square root of 113 squared? Well, square root of 113 squared is just 113. If the left side equals 113 as well, it's a right triangle. That angle is a right angle. So we've got 64 plus 49, which happens to be 113. So I can lift off the question mark and say 113 does equal 113. And that's a big yep. It's a yes. So there will be some problems in your homework where you have to take the 2 smaller sides, square each of them, add them up, and see if it equals the square in the third side. If it does, they're right. It's a right triangle. If it does not, it's not a right triangle. Pretty easy because I think we did this in algebra. So what about this next one? What do you think? 15 squared plus 36 squared, does that equal 4 root 95 squared? And this is why we did that review. How do you do 4 root 95 squared? Well, it's 4 squared times 95, or 16 times 95. What's 16 times 95 equal? 1,520. What is the left-hand side here equal on the calculator? 15 squared plus 36 squared? 1,521. What does that mean? There's a little slash through there, so this should be a note. Man, was it close. Can't we just call it good? Yeah. Well, not if we want a perfect right angle, right? We can't just call it good if we want a perfect right. It's pretty close, though. You're right. Maybe it is close enough. So here's the deal. If the square of the length of the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides, then the triangle is a cube. So here's how to remember this. It says if the square of the length of the longest side is less than, so if you take a right triangle, here's my right triangle, the way I remember it. Here's my right triangle. If the square of the length of the longest side is less than, if this right here becomes less than the sum of the squares of the other two legs, what's that going to do to that right angle? It's going to shrink it in, right? Make it a cube. So as this gets shorter, it will be a cube. And then if it's longer, it kicks it out. Okay, if this is longer, like in this one right here, this is longer, then it's going to kick it out and make it obtuse. And so we have one of each case here. Let's go ahead and just do a quick check here. We can do it 38 squared plus 77 squared. Do it on my calculator here. Let's see what happens on that. 38 squared plus 77 squared. That equals 7373. And then what was it? 86? 86 squared gives me 7396. So that means the longest side is bigger than the sum of the squares of the other two. So go back over here. Over here. So we've got this case right here where the 86 squared is bigger than. It's going to extend that out and make it longer. And so which case would this be? It should be obtuse. Okay. Do you know which of the next two? Why don't you test the next one on your calculator? I'll test it as well. 10.5 squared plus 36.5 squared. So we got 10.5 squared plus 36.5 squared. I already forgot. Yeah, 36.5 squared. What are we comparing it to? 37.5 squared. So now the longest side is actually shorter than the sum of the squares of the other two sides. So that's going to bring it together more. Okay. So when the longest side squared is shorter than the other side, it brings it together, and that gives us our acute one. So there's our acute. And then you'll have to take my word for it. We're about out of time. But if you square 65 and you square 72, it will equal 97 squared. What did we learn is true when the sum of the squares of the smaller legs equals the square of the height? And it's right. So those are your three different cases. So that's it.